Hello, and thanks for checking out this video where we're going to look how we can use a 9-volt battery to generate thousands of volts to make a plasma. So in the last video in this little series, I actually designed the circuit required to convert the 9-volt DC source into a high voltage AC signal. In this video, I'm actually going to build the circuit we designed, test it, and you'll see if things really don't go to plan, but they work eventually, and then we're going to see how we can actually use that circuit we've built to generate a plasma. So with that, let's make a start. So if we want a high voltage from a low voltage source, the standard way to do that is using a transformer. I have such a transformer here. It's basically an ignition transformer from a car or an ignition coil. It's got a few turns on its primary and a lot of turns on its secondary. It's designed to generate high voltages, and if you listen, you can actually hear a liquid inside it. That's an oil, and that gives you a lot of insulation. Don't overdrive these basically, because that oil can boil and the whole thing blows up. I know from a negative personal experience. So I'm not going to use this transformer as a conventional transformer. What I'm going to do is I'm going to use it as a resonant transformer. Okay, so basically there is a turns ratio, so a ratio between primary and secondary turns. I don't know what it is, but I'm not so interested, because what I know is that the secondary coil is basically a massive inductor, and when I connect it to some capacitance via some electrodes or a voltage probe even, and it's actually got some self-capacitance, we actually make a resonant circuit. So if you look at my lectures on resonance, you'll see that basically the resonant frequency is defined by L, which is in this coil, and C, which is probably going to come from this oscilloscope probe in this particular case, and the self-capacitance of the winding. Okay, so I've set up a really simple experiment here where I've connected my probe, make sure I'm on the right channel. I'm going to put 1 volt peak to peak into this transformer, and you can see on the screen we're getting some output voltage of just going above 10 volts peak. Keep in mind, if you can see here, we're putting 1 volt peak to peak in, so there's already quite a lot of gain. Let us now increase the frequency, so 2 kilohertz, 3 kilohertz, 4 kilohertz. You can see the amplitudes going up and up and up. So we're on 8 kilohertz there, and we're probably around the peak. Basically this voltage probe's got quite a lot of capacitance, so when we actually look at trying to generate it with very little capacitance connect on the output, we'll probably see the resonant frequency higher, but in this particular scenario the resonant frequency is around sort of 6 or 7 kilohertz. You can see that's where the peak is. So if you think about that lectures on resonance, if you plot the frequency on the x-axis and the voltage on the y-axis, or the peak voltage, you see a very sharp peak at a specific frequency, and then either side of that frequency it drops away, and that's exactly what we're seeing here. Look, at 2 kilohertz the voltage is really low, just over 10 kilovolts peak or 20 kilovolts peak, and at resonance probably there 6 kilohertz according to this, we're much higher, we're over double that. If I touch this now, should be safe to do so, you can see the voltage drops way off. That's because I've added capacitance, so now if I reduce frequency it starts to go up again, and now the resonant frequency is 2 kilohertz because I've added a massive amount of capacitance. Obviously the peak here is not quite as high as it was before I touched it, and that's because I've actually reduced the Q of the circuit. Okay, the gain is not as high now. If I take that off, the voltage doesn't really change, and then if I increase this now, we're going back towards the original resonant frequency, 6 kilohertz, and you can see the voltage going up. So that's the phenomena we're going to exploit to generate a high voltage, but we somehow first need to turn our DC into an AC signal that can be used to drive this transformer. That's where we need the half bridge. So let's crack on with that. Okay, let's briefly look at the components we need. So we're building a half bridge, so probably the most important component is the half bridge driver circuits, or the half bridge driver IC, which is this component here. It's an IR2153D. Basically does everything we need to switch the MOSFETs at the frequency we want, and it does the high side and low side driving, which links back to what we said about the circuit. So we've got basically our 9 volts is going to come in through the battery clip. It's going to go through this electrolytic capacitor to sort of smooth it out, to sort of stop the voltage dropping when we draw current spikes. That 9 volts is hopefully going to be enough to power this IC, which is debatable. The frequency that this operates at, so that sort of 7 kilohertz we're looking for, relies on these two components. It's basically a resistor or a potentiometer that we can vary, and a fixed capacitance. If we look at the data sheet, we can decide what combination of these R and C we need to get 7 kilohertz. It's got something called a bootstrap, which basically powers the high side MOSFET. That's what enables that to be powered. It basically charges this capacitor when the low side MOSFET's switched. So we can then use that sort of energy stored to switch this MOSFET in the other cycle. These are the two MOSFETs. They're relatively low voltage. I think IRFZ 44Ns. I think there's something like 50 volts, 40 amps, something like that. And here's our sort of capacitive divider. This basically divides the input voltage by 2, and it acts as the midpoint between the half bridge. Again, you have to refer back to the circuit diagram to understand what that means. In terms of tools, I don't really have very much. I have some snips, I have some solder, I have a little tool for breaking the tracks on the board, which I'll show you in a moment, and I have some hook-up wire. This is solid core wire, really easy to put through these holes, which is really helpful. And of course, because I'm going to be doing soldering, I absolutely always wear safety glasses. So whenever I see one of my students without the glasses on, I go crazy, because it's just so dangerous, so easy to damage your eyes with just a little bit of solder. And it's really bad. For example, imagine if you need to take one of these components out, you're trying to unsolder it and you pull it and it can just flick hot solder into your face. Very easy to damage your eyesight there. So I absolutely insist anybody who's soldering in my lab must wear these glasses. So the glasses are on, and really what we need to do first is I always put the IC in, so then we know where the pins are going to be, and I'm just going to aim to stick it somewhere in the middle of the board like this. So let's do that now. I'll break the tracks first. So here, if you look at the board, you can see the tracks are all connected in this sort of vertical direction, and horizontal they're all separate. So we basically need to cut four of these tracks. I'm going to do that now, roughly in the middle of the board. So there, if you look now, the pins are either side of those broken tracks. Looks good. Take my soldering iron. I'm just going to solder one pin on first. Just to make sure everything's nice and aligned, still in okay. Okay, now I can solder the rest. Not the neatest soldering job, but it looks sufficient to me. gap. I don't see any short circuits there. So we just got to note that that's pin 1, that's pin 9, pin 4, pin 5. Okay. Next what I'll do is I'll put all the sort of bigger things in. I'll make a bridge of capacitors. Make these quite far away. So basically, if you think about it, this will be my 9-volt rail. I want these two capacitors joining at the midpoint, and then that's going to be my ground rail coming down here. These need joining together, so that's why I left that big like that. So now I'll solder that there. Snip. Because at the moment those are connected to the IC, so it's kind of vital that they're not. Connected to this middle row as well. Okay, so those are those in. Next we can put the MOSFETs in. Let me just check the data sheet for the IC. So looking at the pin out, this is how we look at it. So pin 1 is the input voltage, pin 4 is to ground, pin 5 goes out to the low MOSFET, pin 7 to the high MOSFET. VB needs a diode from VC if I remember correctly, I need to check that. And there's also a capacitor between VB and VS. So pin 6 needs to go to the source of the higher MOSFETs. Okay, let me just sort of wire this up. Okay, I'm going to solder that MOSFET there for now. So when I'm soldering MOSFETs like this, I like to just solder one pin first and then flip it around, and you'll see it's kind of all horrible. So I'm just going to put a little bit of pressure on and warm that pin back up and then straighten that MOSFET. Just got to be careful there not to burn your hand. So now basically the source of that MOSFET, this third pin here, is connected to pin 6 on the MOSFET driver. I'll have to break the other two tracks. Then we need the other MOSFET putting in. Put that here, where that source is going to go to our ground. You may be thinking, hang on, how are you going to heat sink these two MOSFETs? And the answer is, I'm not going to bother at the moment. You know, we're running from a 9-volt battery, we're not going to be running much current through this, and we're probably going to run it for a few seconds max. So in that sense, we won't need heat sinks. It's not good practice though, if you're doing that in something that's going to run for more than a few seconds. It must be heat sinked. Okay, so there's my two MOSFETs. Basically I've got my full bridge now. Here's one side of the bridge, there's the other side. Looks okay. Okay. So before I forget to do it and destroy the MOSFET driver, I need to break these two pins. So it's pin 6, I need to leave. So let's pop this one in. So this is an electrolytic, so it's polarized, so I need to make sure that I get it in the right way. Okay, just need to make sure that's on the correct rail. No, it's not, it's one short. Now it's connected. So basically this is going to be where my 9 volts comes in, so this is the positive side of the electrolytic, and if you follow it along that track, it connects to that part of the capacitor, that top leg of the capacitor. Okay, so that's done, and I'm going to put my bootstrap components in now. Let me check the data sheet again. So if you look at the recommended circuit, it goes from VCC, a diode, to VB, and then a capacitor from VB to VS. So in other words, from pin 1 to 8 I need a diode, and then from 8 to 6 I need a capacitor. Okay, here's my diode. I'll put it above the MOSFET, and I just need to connect the wires together then. Add some wires. I'm not a fan of bending the pins like that to help solder it, because it makes it really difficult to get out, but I don't see an option not to do that at the moment. Obviously that diode's doing nothing at the moment because it's completely shorted out, so I need to break the track. And I will just bend that pin down and down there and solder it. So now pin 1 and 8 are connected together via a diode as per the datasheet. That's a bad move. So there I've bridged some tracks I shouldn't have done, so I'm going to need my solder remover. Should have cut the thing shorter first. I'm not entirely sure if I've connected pin 1 and 2 together there, which would be a problem. Let me get a multimeter. Let's have a multimeter. Check if they're connected. Yep, okay. So my concern is in pin 1 and 2. Are they joined together? They are, but that's 1 and 2. No, they're not joined together. Check the other side. No. They're not connected together. Good. Messy, but it's acceptable. So let me put this bootstrap capacitor in. Unfortunately I don't have a wide selection of capacitors, so this is the best one I can do. So this needs to go from this, basically this diode to pin 6. Okay. So other than the two timing components, which I may as well put in now. So basically, let me have a look at the circuit diagram again. RT goes to CT and CT goes to ground. Okay. I'm not going to solder in RT at the moment because then I'll have some wires and that potentiometer floating around, so I'm not going to do that. I'm just going to put a capacitor from CT to ground. So pick this capacitor without very much thought on what it actually is, and I'll sort it out with the resistors basically. I'm just going to put it in where it fits and I'll break the track. Messed up, I put it in the wrong hole. I put it in basically the ground there. That wants to be the one above it. Not so easy to unsolder. Needs to go into pin 3, and that was pin 4. Pin 3 is that pin. Okay, that's most components in now. Let's add some wires. So, for testing purposes, I'm going to use a power supply anyway, my DC power supply, so I will just add flying leads to connect the power. So power connects to that capacitor, that ground connects to that source and that capacitor. Okay, so I need to join the two MOSFETs together. The capacitors are already joined together, and then the bridge is sort of complete. So to join these two MOSFETs together, we need to go from the source of one of the MOSFETs, the top MOSFET, to the drain of the lower side MOSFET. can see immediately I'm going to have to cut some tracks there. Basically the ground capacity, the capacitor which is now grounded, is actually connected to some kind of part of the MOSFET. It looks like the gates. So immediately I'd break the MOSFET driver if I switched it on in its current format. So that is the gates from the MOSFET. Let's break that here. Okay, that looks okay. So let's do the power for the MOSFET driver. So power's on pin 1, which is there, and it needs to go up to this rail. Something like that. Okay. Other than the potentiometer, I believe that's done. So I've got a 10k potentiometer here. Nothing shorts out a circuit board like little broken bits of metal. So for this, I'll use my oscilloscope DC power supply. Okay, so now I think I'm ready to test this circuit out, so I'm going to connect my oscilloscope probe and I'm going to connect it to basically the middle of this half bridge, which is there. There's no easy ground here, which is annoying. I'm just going to leave it floating, see what happens. Definitely not going to be getting 9 volts of division out. Right, and I'm going to gradually turn up the voltage around 9 volts. It should kick into life. Huh. I would say no, it doesn't. The waveform looks absolutely disgusting, like it's driving a short circuit. Good news is the frequency is about right. there's definitely a problem there. It's not the beautiful square wave I'd be wanting. Let me check. Well, firstly, let's do a proper ground, because that's just stupid. Try it again. Nope. Less noisy, but still rubbish. Obviously it shouldn't look like this. There's clearly an issue. Well, it looks like there's an issue at the switching side rather than the timing side of that MOSFET, so let me see what's going on here. All looks okay. Capacitor goes from there to pin 6. Pin 6 is there. That looks okay. There's a break there. High side gate driver. Comes out of pin 7 into the high side, that's correct. I've missed possibly the most important wire of the whole board. It's the one that actually connects the high side MOSFET to the DC voltage source. So if you think about it, the drain of this MOSFET here needs to be connected to the 9 volts. Like that. At least that was a nice little try to see if the frequency's working okay. We're at the right switching frequency and it looked promising. Kind of a major wire not to put on the board. So, after some additional fault finding and a massive amount of swearing, finally got to the root cause of why this thing wasn't working, and it's the most infuriating thing I can imagine. The MOSFET driver was dead. So basically I spent a long time, I changed the diode, I tried a load resistor, I checked every connection and just nothing seemed to explain why it wasn't working. So really I boiled it down to the only logical explanation left is that the MOSFET driver is not working properly. And of course I swapped it out, which was a pain because it's difficult to unsolder those 8-pin dips, and of course it works beautifully now. You can see a square wave on the low side MOSFET drain, and it goes down to around 7.4 kilohertz. Okay, so really the next thing is to connect the high voltage transformer, which needs to be done with great care. So I'm turn that down. Obviously I won't be able to use my low voltage probe for this, it's way too low. Take my load resistance off, that was just a 5k resistor I put in there for troubleshooting. So obviously I can't just use my little sort of low voltage oscilloscope probe to measure the voltage out from this high voltage transformer, it will break immediately. What I do have is a rather large high voltage probe, max 18 kilovolts DC, and it divides by 1,000 times. So let's plug this in and sort this all out. Plonk that down there for now. That's the ground. Okay. Right, let's turn it on. Okay, we can immediately hear high voltage. So, at the moment, you can see on the oscilloscope, I'm going to knock the green off, we don't really need that anymore. This is the output voltage from the transformer. It's on 1000 volts a division, so we're getting a peak to peak voltage there of 4 kilovolts peak to peak. But if I now, and I'm putting around 9.6 volts in, but if I reduce that frequency, look, we can clearly see a resonant peak there, around 13 kilohertz. So you can see the DC power supply is off, and I'm going to go and find my 9-volt battery now. We should see something on the oscilloscope. I'm just going to ground everything. Okay, so when I plug this in, we should see some volts on the screen, eh? As you can see, there you go. I'm not sure why that's not triggering, probably because it's there's no reference to the actual voltage source here. But as you can see, it's still making 6 kV peak to peak. That should be enough for what we want. Nice. So already you've seen we've gone from 9 volts to 6,000 volts. Let's see if that's enough to do with what we want to do. So here I've set it up battery powered, and I've got an actual gas flow coming out of this tube. It's an argon gas. Fortunately I don't have any helium, because that would be easier to break down. But as you can see, you get a really nice plume coming all the way out. It can go for maybe 2 centimeters. Oh, that's a lot longer, 3 centimeters. Wow, that's pretty cool. Fortunately, it doesn't self-sustain. I'd obviously need a little bit of a higher voltage, I think. I'm only getting around 6 kV here, which is a shame. I can't actually get that to work. Clearly, I don't want to put my fingers in there and get a shock. Let me play around with the potentiometer now. No, that's making it worse. No, I've definitely got the optimum. Let me try redesign the jet. And there you go. Let me go knock all the lights out. That's pretty cool. And there you can see an argon plasma jet. You can put our little wire into it. And if we're feeling really brave, trying to get a bit different angle. Doesn't even feel hot. I imagine my battery's going down really quickly. Doesn't want to focus. You can see it becomes a lot more intense. And if you don't believe that it's cold, look at that, you can see the fluorescence. Obviously it's not burning. Put it there, it might burn. No. Yeah, it's amazing. Not very stable, but it's right on the voltage threshold.
So just to summarize this video, we made a simple switch mode power supply to drive a resonant transformer from a 9-volt battery. Using the high voltage output from the transformer, we actually generated a non-thermal argon plasma, and as you saw in the video, I was able to put my fingers in it and didn't get burnt, so that's pretty cool. In the next video, which is going to take a few weeks to come out, I'm actually going to design and build a voltage multiplier which will take our output from our resonant transformer and turn it into sort of tens of thousands of volts DC, which we'll then use to charge up a Marks bank to generate some seriously high voltages. So this is where we go from basically high voltage, low current to actually involving capacitors and charging them up, so things become a lot more dangerous, but the voltages we can get are a lot higher. So with that, I hope you enjoyed the video. Thanks for watching. If you have any questions, please put them in the comments, and please do like and subscribe because it really helps the channel. So see you in the next one.